Okay, perfect. Let's start this new build session. We're gonna learn how to write a smart contract using one of the repos from the OpenZeppelin team. It's called Midnight Apps. So first, let's understand why OpenZeppelin on Midnight matters. OpenZeppelin secure over $100 billion in Ethereum smart contracts. Their contract libraries are the standard ERC20, Access Control, Ownable. Every serious Solidity developer has used them. So now they are building for Midnight. First, reusable CK contract libraries for a privacy-first blockchain. Let's see what they have built. Access control, shielded ERC20, math libraries, utility patterns. A product that they have demonstrated with these libraries. It's called LunarSwap. It's a working DEX on Midnight pre-prod that uses all of this. And why it matters is because OpenZeppelin builds for your platform. It signals something really interesting. It means that we are ready for real development. Okay, let's go through what we're gonna learn during this session. We're gonna learn how Merkle trees replace mappings for private role management, how shielded tokens work on Midnight's native coin infrastructure, the witness pattern of chain compute on chain verify, how the LunarSwap DEX wires contracts to a Next.js frontend. In this case, we're gonna be using Vue.js. Okay. In the video number 7, the build session number 7, we built a simple bulletin board. Today we're gonna look at a production grade contract pattern from the team that defined these contracts. Okay, so before we go deep into other aspects, we first need to understand the architecture, how everything connects. So for that, we have this diagram here, where we have divided everything on layers. For the layer 1, we have the smart contracts. On layer 2, we have some compact tools that are sub-modules. And on layer 3, we have the actual application. So in layer 1, we have access control, shielded ERC20, math, which are imported by LunarSwap contract. Then on layer 2, we have compact tools, sub-modules, compact compiler, compact builder, CK circuits, TypeScript bindings, witnesses. All this is the part that glues the output of the compilation with the actual application. And then for the layer 3, we have the actual application, the UI part. We have the wallet context, lace connector, auto reconnect, network context, testnet, mainnet switching. There are the different networks able we can define in this application. We have components for the UI part, for example, the swap cards, the token input, the pool management, and then we have infrastructure. Lace wallet with the browser extension when we are working in the UI. We have a proof server, we're using Docker to host that server, Midnight pre-prod testnets, and the indexer. Okay, we have the repo here. But let's see how that repo is organized, is structured. Different developers have different ways to put the code within a mono repo. But in this case, let's take a look how the team of OpenZeppelin structured the LunarSwap application. We have a contract folder where we have compact contract library, access, shielded token, math, struct. These are the modules. Then we have a compact contract. These are Git modules, just a reference. Then we have compact tools that are Git modules, compiler, builder, CLI. And then we have the folder for the actual application, LunarSwap UI. This is the front end. And then we also have some packages, shared configs. Okay, now let's understand how this access control actually works. Before going deep into the details, let's see the diagram, understand the flow. So we have an escalator that is going to give us a better picture of how this works. So for the grant role flow, we have a user and a role that is a private information. This part here. this part here. Then we calculate a hash, a persistent hash, and then we put that in a commitment. And that commitment, it's gonna be included in a Merkle tree. So that's the way we grant a role, right? This is public and this is private, but the hashing makes that private information actually private, even though we're gonna put the commitment on the public side. For the nullifier flow, we have again a private witness where we're gonna get a secret key, and we're gonna calculate the nullifier by hashing it using the secret, the user, and the role. And we're gonna place that commitment, that hash, into a set. So this is gonna be public and prevents duplicate grants. And then we have the hash role verification. How we do that? We're gonna recompute the commit, the hash. Then we're gonna use the oracle, the private information, to calculate the path. We're gonna pass that to the smart contract that is gonna check the root, and the result is gonna be a boolean saying, okay, that user is authorized or it's not authorized. So at the end we have something that goes on chain and something that it is stored off chain. On chain we have commitments hash, nullifiers, Merkle tree roots, insertion index, and in the private of chain we have user identity, role assignment, secret key, Merkle path. So let's see the code itself, some snippets. So in the case of the ledger state, we are defining some variables. We have its initialize, it's of type boolean, it's a one-time init guard. The reason that we're using that is because everything is being declared within modules. So once we construct our main contract, the way we initialize every module is by using this variable here. So it's initialized. Then we have role commits. This one, it's a Merkle tree of depth 10. So that means we're gonna have 1024 role slots. So this is actually our Merkle tree. And then we have a role nullifier that it's gonna be of type set of bytes 32. This is where our commitments are gonna be stored. Prevents duplicate grants. And then we have our index of type counter, and this is how we're gonna declare the index, the next index for each commitment that is inserted into the Merkle tree. So why a Merkle tree instead of a mapping? On Ethereum, mapping, address role, it's fully public. Everyone sees who has what role. With a Merkle tree, you start hashed commitments. The commitment, it's on chain, but you can't reverse it to learn the user or the role. So that's the reason why we're using Merkle trees. It's an important feature that we can use with Midnight. Then we have some roles that is of type enums. And what roles we have? We have admin, LP, trader, and none. For roles, none is a default. LunarSwap uses admin, LP, and trader. Okay, we have then the circuits themselves, the one that we were talking about. Now we have grant role flow. So how do we define that using compact? So we can see here different functions. Let's take a look at them. So first we have this grant role, where we're passing a user of bytes 32 and a role of type role. That role, it's an enum. We have defined that just before. So then we make sure that it's only the admin, and if that passes, we can grant a role. So the caller must prove admin role. So this grant role, it's defined here in another circuit. So you can see how a circuit can be embedded into another circuit, like functions calling another functions. So this grant role, we're passing a user defined with bytes 32, a role of type role, it's an enum, and what we're doing inside, we're calculating the hash of this path with index access control. We're passing the user and we're passing the role. So at the end, this is the commitment. It's a hash of something which means it's the commitment that is going to be inserted into a Merkle tree, for example, or a set if it's the nullifier. Okay, so now we want to calculate the nullifier. We're going to run this function, persistent hash. That's a function that we have available in the standard library. And then we're passing the path 32 with this index access control nullifier. We're passing the witness get secret key. This is an oracle function. We are getting that information from our private part, private information. Then we have the user, and then we have the role. So by running this persistent hash, we are actually calculating the nullifier. So the secret key from witness equals the nullifier. Then we are doing an assertion. What we are comparing here, we're making sure that the role nullifiers, the nullifier is a member of this set. So reject if it's already granted. This is the part that we're saying, okay, we want to make sure that we're only giving one role to a specific user. If it does have that role again, we're gonna reject that. So we use assert within Midnight contracts to actually make sure that something complies to a specific logic. And after all these passes, then what we are doing is actually updating the state of our smart contract. In this case, we are inserting the commitment in the tree, and then we are recording the nullifier on chain. Here it's not the actual code, it's just a representation where we are saying the commit now it's gonna be this insert, and the nullifier it's gonna have this new insertion of the nullifiers. So you can see here that we are inserting something into the set, and we are inserting something into the role commit. So we are updating the smart contract, and then we are incrementing the index, and then we are calling a private oracle function that actually updates our private state. So the pattern is the same. We calculate things, we make sure that the condition complies, and if everything passes, then we update the state of our contract. So here is a summary. What's happening? Hash the user role into a commitment. The role data stays private. Generate a nullifier using the secret key. Prevents double granting without revealing what was granted in the first place. Insert the commitment into the Merkle tree. On-chain but opaque. Update private state through the witness. The witness tracks which roles map to which commitments. Okay, this is another circuit, has role verification. So now we want to verify that something is complying within the Merkle tree. So the way we do that, we're defining this hash role, and again, we are calculating the hash. So we're gonna have our commit, recompute the same commitment, and now we want to actually calculate the path to then assert something within the contract. So with this witness function, what we are doing is calculating the path of chain, and then making sure that we're gonna have the Merkle path and the Merkle value. And with those values, what we are doing is we are asserting that the role commits verifies to those values. So we are verifying the path against the on-chain route. This is just representation code to understand what's going on, right? The important part here is we're calculating the hash, we're calculating the path of chain, and then with that we can verify in the circuit that something complies. So the CK magic, the circuit proves you have a valid Merkle path to a commitment in the tree without revealing which commitment, who the user is, what the role they hold. The verifier only learns, yes, this person has the role they claim. Okay, and we have been talking about these witness functions. So as a summary, we have talked about these three ones. The witness update role, get role Merkle path, and get secret key. So you can see that a function, it defines something that is going to be run off chain. That computation can be just getting a value stored on chain, but we can actually update our private information. So the private part it's actually a kind of a database, right? That it's stored off chain out of the blockchain itself. So this update role stores the role assignment in local private state. The get roles Merkle path, it retrieves the Merkle proof path for verification. And the get secret key, it provides the user secret key and it never touches the ledger. So we have the summary that we talked before in the architecture diagram in Scala, where we define what's on chain and what's off chain. So as a summary again, on chain we have the commitment hash, the nullifier, the Merkle tree root, and the insertion index. And in the off-chain part, we have the user identity, role assignment, secret key, and the Merkle path.